Hello friends, welcome to Mu Lessons. Today I am here with my favorite topic. This is one of the most interesting topic of physics, that is the quantum theory. So we'll see what is quantum theory and why it came to existence in this world. So first of all, starting with the basics as usual, what is quantum theory? This is a theory needed to describe physics for the microscopic scales, that is for the atoms, molecules. These are so small in size that classical mechanics is not applicable on them. So, to solve their problems, we have to introduce quantum mechanics. Now, previously we have learned about the classical theories like the Newton's mechanical motion of objects, where you have seen F equals to m into a, or Maxwell, who treated light as a wave. But all the problems were not solved by these classical theories, so quantum theory came into existence. These classical theories are not suitable for the microscopic particles like the atoms, molecules, and hence they can be solved by the new theory which we will learn today, that is the quantum theory. Any of the very small increments or parcels into this many forms of energy are subdivided. So we can say light is a form of energy, is a quantum of electromagnetic energy. It is formed into packets known as the photons. So either it is a wave or particle. This is a very doubtful question. Even you can see this picture. This is a photon who has two visions in his mind, that am I an X-ray photon or a radio photon or visible, or it is a particle. So also we are also in doubt about whether these photons behave as wave or particle. Now in some cases it is suitable to treat them as a wave, and in some cases as particle. So there is a duality, we say it a wave particle duality. It has both the natures, that is the wave nature and particle nature. Now let's start with some basic knowledge about light waves. The classical wave theory of light described most important phenomena, that is the amplitude, wavelength, frequency, and the energy of wave was given by the amplitude square, that is the square of the amplitude gave the energy of the wave. And there are some features like amplitude, frequency and wavelength. These are the basic characteristics of light waves. Then there was a problem in the mid of the 20th century. Several effects were observed which could not understood the wave theory of the light, like the Einstein's photoelectric effect and the Compton effect. So these two effects, or you can say these two observations, did not follow with the wave nature or the wave theory of the light. So we'll describe each of these today, what happened actually in these two effects. So first, coming to the photoelectric effect. According to the classical mechanics, we have seen the energy of the wave depends upon the amplitude, or you can say the directly proportional to amplitude, or equals to the square of the amplitude. So by increasing the amplitude of the wave, the energy of the wave should increase. So in this case what happened? A certain amplitude of wave was emitted, but it could not cross this block. Again, according to the classical mechanics, the energy depends upon the square of the amplitude. So again some more amplitude wave was thrown and it also did not pass. And now some high amplitude of wave was also given, but it also failed. That means electrons did not emit from this metal surface. This block is treated as a metal surface, and whenever, according to photoelectric effect, whenever a ray of light falls on this metals, photons comes out. But in all these three cases, by increasing the amplitude from very small to little quite larger, there was no emission of the electrons. Now let us try with something different. We keep the amplitude constant. Now we change something else, that is we'll change the wavelength. And changing the wavelength will change the frequency of the wave. You know it very well. So for the first case, we have the same magnitude, but electrons were not emitted. Keeping the magnitude same, we change the wavelength, that is we increase the frequency. There was some emission but with low kinetic energy. Now with some more frequency there was an appreciable emission of these electrons from this metal surface with higher kinetic energy. So what do we conclude from this part? No electrons were emitted until the frequency of the light exceeded the critical frequency, that is called the threshold frequency of the metal. It is unique for a particular metal. At this point the electrons were emitted from the surface. Whenever the energy of the light is more than this threshold frequency, the electrons are emitted. So for larger frequency we have seen the emission of electrons. Now electrons are attracted to the positively charged nucleus by the electrical force. In metals the outermost electrons are not tightly bound and can easily be liberated, or you can say they can be easily taken away from the orbits. It just takes sufficient energy. Now according to classical mechanics, we increase the energy of the electromagnetic wave by increasing the intensity, that is brightness. Suppose we increase the amplitude of this light, then it will be more bright obviously, and we know energy is directly proportional to amplitude square. But does it really help in emitting the electrons from the, or taking away these electrons from these orbits? No, it doesn't work. Now we have to think in a different way. Rather we have thought till date that till this time that wave nature of this photons, but now we will treat it as a particle. So the alternate view of this light was to act like a particle. The light particle must have sufficient energy to free the electrons from the atoms. So increasing the amplitude is simply increasing the number of light particles and nothing else. But it's not increasing the energy of the waves. And this was said by Einstein. So by increasing the amplitude did not work, but by increasing the frequency it really increased the energy of the wave, and hence we get the electrons out of the orbits. With lesser energy we will get the kinetic energy of the photons small, and with higher frequency, or you can say with higher energy waves, we will get high frequency of high velocity or high kinetic energy of electrons emitted from the metal surface. Now in this quantum mechanical picture, the energy of the photon must overcome the binding energy of the electrons from the nucleus. If the energy of the photon exceeds the binding energy, then electrons will be emitted. So this is the simple equation, that is the kinetic energy is equals to energy of the photon minus the binding energy. Whenever the energy of the photon is greater than the binding energy, the electrons will be emitted with a particular kinetic energy. And in this case the energy of the photon is given as E equals to h nu. You know it very well. H is the Planck's constant, 6.6 × 10⁻34 joule per second. Now suppose the light before collision and the light after collision, the electrons are emitted. With higher frequency of wave or the higher energy, it is easy to emit or take away the electrons from the orbits. Now previously we have thought these photons to behave as a wave nature, but this quantum theory describes light as a particle called the photons. According to the quantum theory, a photon has an energy of E equals to h nu, or you can substitute nu equals to c by lambda, so we get E equals to h c by lambda, and hence the energy of the light is proportional to the frequency and inversely proportional to the wavelength. The higher the frequency or lower the wavelength, the higher is the energy of the photon. Now for just analysis view is one point. 10 photons have an energy equal to 10 times single photon. So in these types of cases, classical mechanics failed and we came with a solution with the help of the quantum mechanics. Now in this case also the electromagnetic spectrum, the shortest wavelength more energetic particles, so we conclude like this. Where the shortest wavelength, that is the frequency were high, that is the gamma rays and X-rays, they are the most energetic waves or the most energetic photons, and coming down to this spectrum, through this spectrum we will find the radio waves having long wavelengths, and these are the less energetic the photons. The energy of these waves are also given by E equals to hc or E equals to hc by lambda. Sorry, E equals to h nu or E equals to hc by lambda. Now in physics there is another quantity, that is the momentum. Momentum, you know, that is mass into velocity. It is a scalar. Unlike energy, which is a scalar, momentum is a vector because it has got directions. In its direction is given to the direction of the velocity vector. Now the reason it is important in physics is because, like energy, total momentum is always conserved. In case of physics, we always assume the conservation of energy, so in this case also the momentum should also be conserved. Now there is another question: do photons carry momentum? Now one of the greatest scientists, de Broglie, proposed that a photon did not only carries energy but also momentum, that is P equals to mv, and photons have m equals to 0, mass equals to nearly 0, so how can it be that the momentum is not 0? Now de Broglie postulates that the photons carry momentum and the momentum is given as P equals to E by C, or this momentum is given by Planck's constant by the wavelength h by lambda. So you can see this de Broglie's relations, P equals to h by lambda, photons, which conclude that the photons carry momentum, and we have E equals to hc by lambda previously, and this shows that photons carry energy. So we conclude that both energy and momentum are inversely proportional to wavelength, or they are directly proportional to the frequency of the wave. The highest energy photons are those which have the smallest wavelength, like the gamma rays. That's why the gamma rays are so dangerous to us, because of the high energy. Now coming to the second problem, that was the Compton effect. In this case, incident X-ray of wavelength lambda 1 was emitted and strike to the matter. Now in this case there was some electrons coming out from the matter. So according to the wave picture of light, the incident X-ray should give up some amount of energy to the electron and emerge with a lower energy. That is, the amplitude should be less, but it should have the amplitude same. But it didn't happen in this case. It was found that the scattered X-ray did not have the same wavelength as the previous one or the incident one. In this case also, quantum picture came to rescue. With the help of quantum mechanics, this problem was solved. The incident X-ray was having energy E1 equals to hc by lambda 1, and the electron was initially at rest, almost rest. Now when that hit the particles, when this incident hit the matter, there was two things happening, that is a scattered X-ray having energy which is equals to hc by lambda 2, and in this case lambda 2 was greater than lambda 1, and also there was emission of these electrons. So Compton found that if you treat the photon as the particles of zero mass with energy E equals to hc by lambda and momentum P equals to h by lambda, the problem was solved. The collision behaves just as two billiard balls colliding with each other. You can see this, like one billiard ball strike at the middle and they get scattered away, the other billiard balls. So this is just a diagrammatic vision of understanding. So this shows that the photons behave as a particle with energy and momentum, and the photoelectric effect also gave the same conclusion. So what do you sum up about these photons? They can be treated as a packets of light, that is the particles. To describe the interaction of light with this matter, one generally has to appeal the quantum description of the light. So it has energy equals to h nu or hc by lambda. All the variables are known to you. Now it has a momentum that is given as P equals to h by lambda or E by C, you can say. So finally what we get? What is light, a wave or a particle? Is still confusion for that same photon. On macroscopic scale we can treat the large amount of photons as a wave. Remember, on macroscopic scales only we can treat them as wave, but while dealing with the subatomic phenomena or single photons on microscopic scales, we need to treat them as a particles. So this was the basics about the modern physics and the first step to quantum theory. So we will come up with some more videos on this quantum theory regarding the particles in a box and so on in the next video. Hope you like this video. Thank you. All the best.